Software is pretty much everywhere you look, from the apps on your phone to the massive systems that, well, run our world. But have you ever stopped to think about how it's actually built? Today, we're going to pull back the curtain on software engineering, and we'll look at how we went from, let's say, chaotic coding to a real structured craft. All right, let's dive in.
But first, let's start with a question that I bet every single one of us has yelled at a screen at some point. Why is it so darn hard to build good software? I mean, come on, we've all been there. The app that crashes right when you need it, or that new feature that's been coming soon for like 6 months. You'd think it would be simpler, right? Well, it turns out this is not a new problem at all. In fact, it's a really old one. It even has a name.
Yep, they called it the software crisis. This term popped up way back in the 1960s, and it described this period where our ability to build solid, reliable software just couldn't keep up with the amazing new computers we were building. The hardware was getting super powerful, but the software, it was falling way, way behind.
Okay, so this image does a fantastic job of showing the pressure cooker that created this whole crisis. Think about it. Pushing down from the top, you had this explosion of demand for more software. Plus, the stuff we wanted it to do was getting way more complex. But what was pushing back from the bottom? Well, you had a workforce that wasn't really growing, methods that were totally stuck in the past, and basically the same old tools. It was a recipe for disaster. A perfect storm, really.
And the results? They were pretty much exactly what you'd expect. And they were painful. Projects just kept going way over budget. Deadlines weren't just missed, they were completely blown out of the water, sometimes by years. And even if, by some miracle, a project was finished, the quality was often just awful. And we're not talking about small annoyances here. This stuff led to some catastrophic failures. I mean, look at the Mariner 1 space probe, lost forever because of one tiny mistake in the code. One.
The legendary computer scientist Edsger Dijkstra, he just nailed it with this quote. He said, "Now we have gigantic computers, programming has become an equally gigantic problem." And that's the key, right? As the hardware got more and more powerful, the job of programming it didn't get any easier. In fact, it got harder. This wasn't just about banging out code anymore. It was about wrangling this insane level of complexity. Something had to change.
So what was this big new approach? Well, it was a totally new way of thinking that we now call engineering for code. The big idea was to take all the discipline, all the structure, all the proven methods from traditional engineering, building bridges and stuff, and bring it into the Wild West of software development. It was time to bring some order to the chaos.
And, a really crucial place to start is just understanding what we even mean by software. Because it's not just the code. It's not just a program that tells a computer what to do. Real software is the program plus all of its documentation. We're talking about the user manuals, the design documents, the test plans, the whole shebang. Without all that stuff, a program is just a fragile, lonely piece of code. It's like having an engine with no car around it.
In this visual, it just illustrates that idea perfectly. You see, you've got the code over here on the left, that's the program itself. Then in the middle, you have all that critical documentation explaining what it does and how it was put together. And then over on the right, you have the manuals that actually teach people how to use it. You absolutely need all three of these pieces to build professional, truly reliable software. So the big question is, how do you possibly manage all of this complexity? The answer is simple. You apply engineering principles. You bring in a system, you use proven tools and methods, and you bring order to that chaos. It's about having a predictable, structured way to guide the whole process from day one all the way through to maintenance.
But here's the thing. Software engineering is kind of weird. It's different. See, conventional engineering builds physical stuff, right? Bridges, cars, things you can touch. But software is completely intangible. A bridge gets old and wears out from physical stress. Software doesn't wear out. And that makes it way more flexible. Imagine trying to change the blueprint for a skyscraper when it's halfway built. That's a nightmare. But changing software, it's much more possible. Though, believe me, it's still pretty complex.
These two images really drive that point home. On one side, you've got manufacturing. You're churning out physical things that are eventually going to wear out and break. But software, it's developed, not manufactured. It's designed, it's crafted. A bug in your app isn't a manufacturing defect, it's a flaw in the original design. And while the code itself doesn't physically get old, it can absolutely become obsolete. We call it software rot, where the world and the technology around it just changes so much that the old code just doesn't work well anymore.
Okay, so how do engineers actually do all this? How do they put these principles into practice? Well, they use a structured process.
Think of it like a roadmap. It guides the entire project from just a little spark of an idea all the way to a finished, working product that people can use. And this whole roadmap has a name, the software lifecycle.
All right, so here's a kind of simplified look at that roadmap. We call it the Software Development Lifecycle, or for short, the SDLC. It's all about providing a clear, structured flow to get from A to B. It breaks down the massive job of building software into 4 main stages: requirements, design, testing, and finally, maintenance.
Let's kick things off with step 1, requirements. And honestly, this might just be the most important part of the whole thing. This cartoon just says it all, doesn't it? Trying to get a crystal clear picture of what a user actually wants is so hard. The whole game here is to translate vague human ideas into super specific technical instructions. If you mess this part up, well, your entire project is built on a foundation of sand.
Okay, so once you know what you're building, the next logical question is, how are you going to build it? That's where design comes in. This is the blueprint stage. You wouldn't start building a house without a detailed blueprint, and it's the same exact idea here. This plan maps out everything, from the big picture structure of the whole system all the way down to the nitty-gritty details of how every tiny piece is going to work.
All right, the code is written. Time to ship it, right? Nope. Now it's time for testing. And let me be clear, this is not just about randomly clicking around and hoping you find something wrong. Oh no, this is a systematic, organized hunt for bugs. Teams will test the tiniest little pieces of code on their own. We call that unit testing. Then they test how all those little pieces play together. That's integration testing. And finally, they test the whole system from top to bottom to make sure it actually does what it was supposed to do in the first place.
And finally, a lot of people think the job is done once the software is launched. Not even close. The work is never really over. You have to think of software as a living, evolving thing. The maintenance phase is where it actually lives its life out in the real world. And honestly, this is usually the longest part of its entire life cycle. It's everything from fixing bugs that users find, to making it work on new operating systems, to adding awesome new features that keep it useful for years and years.
So after going through all that process, requirements, design, testing, maintenance, what's the point of it all? Well, this whole structured approach is designed to do one thing, and one thing only: build better software. But what does better software or high quality actually mean? It really boils down to a few key questions. Is it correct? As in, does it do what we said it would do? Is it usable? Is it actually easy for people to use? Is it reliable? Does it work consistently without crashing all the time? And finally, is it efficient? Does it use your computer's resources without slowing everything down? A good engineering process aims to check all of those boxes. So when you put it all together, the big takeaway is this: that systematic, disciplined process of software engineering, it's like the invisible engine that powers our entire digital world. It's the thing that takes a chaotic, brilliant idea and transforms it into the stable, reliable apps and systems that we pretty much take for granted every single day. And that really leaves us with one final thought to chew on. The next time you open up an app and it just works, it's seamless, it's fast, it never crashes, just take a second and think about all that invisible engineering humming away just beneath the surface. Think about the blueprint, the testing, the sheer discipline that went into making it feel that effortless. What are you taking for granted?